Is my screen visible to everyone? Okay. So what we have discussed in previous lecture about micromeritics and rheology, where we left, we have discussed about the density measurement and surface area measurement, right? What are the different methods for measurement of surface area and what are the different methods for density determination? Come on, guys, answer fast. Air adsorption, yes. And air permeability, yes. Very good, Manisha. Right? So because it's very important, because that two topics are very important, because almost every year the question has been come from that two topics, right? Density measurement and regarding the particle size measurement, right? We'll see that in brief also, right? So what is micromeritics is that we measure the you can say particle size in general. If we talk about the solid forms, like solid state, like some particles like drug particle API, we have a API powder, right? So we measure the its size, its diameter, different types of diameter. We will study different types of diameters and their definitions. They are also important, right? So we will start with the different types of diameters and their definitions. So first one is mean particle diameter. Okay. So what is mean particle diameter is the mean is the sum of the all individual diameter divided by the number of particles. So simply, if you know about the ocular micrometer and stage micrometer, right? So we'll use that for the measurement of the individual particle diameter, right? We attached it with the optical microscope, and then we will measure the individual particle diameter, and then we average it. That is simply mean particle diameter. Okay, then we have a median diameter. So it is very kind of a very similar to mean median mode, but they have just attached a diameter term because we talking about the diameter, right? So the diameter for which 50% of the particle are less than the stated size, it is preferable to mean diameter as a single measurement of particle size. So simply a median, right? So the 50% of the particle 50% of the particle are less than a stated size. It means it means that, for example, a particle size is 13 micrometer. So if this is the median, it means that, for example, there are 100 particles, right? So the median is 30 micrometer. So 50 particles will be below 30 micrometer and 50 particles will be above. So that is the median diameter. Okay. Then there is a mode diameter. So in this 100 particles, from 100 particles, how many are or you can say the particle with the highest number of in diameter. Like for example, if the 30 micrometer particles are 25 in number and others are in 10, 15 or 5, that is the number of other particles. Okay, it means that 20 in range of 30 micrometer, 25 particles are there. So this is the highest number. So that is the mode diameter. Okay, 30 micrometer will be mode diameter. I am just giving the example. Okay, so this is considered as a mode. Okay, so this is mean particle diameter, median particle diameter, and mode diameter. So now very important some more definitions about different types of diameter. Okay. So this is also this image you may have seen in the Martin's Martin book for the physical pharmaceutics, right? For the Martin reference book for the physical pharmaceutics. So the first is the projected diameter, projected area diameter. So what is projected area diameter is that the distance between this two. Okay. This is shown in figure. So this is projected area diameter. Okay. Simply they are measuring the area between this. It is written here. So that is projected area diameter, and projected area diameter we identified from which method? From which method we can identify projected area diameter for the particle size? Microscopic. Very good. Very good, Vivek. Yes. So through optical microscopy, whatever kind of diameter you are measuring, that is projected area diameter through the optical microscopy. Okay. Then we have a ferrite diameters and Martin diameter. So ferrite diameter is this bisect, this line. Okay. This line which I am highlighting, this is known as a bisect. So this diameter is known as Martin's diameter, mean chord length of projected particle perimeter, which means this is also one definition. And if you read it in Martin's book, they have written it as a you can say as a bisect. It means that it is dividing the particle into half. It is they are imagining that it is as a you can say spherical particle, right? All particles are not spherical, but here they are imaging, and based on that they are giving the definitions. Okay. So in case of Martin's diameter, Martin diameter is the distance, or you can say this length is of this bisect. It is written in the Martin's book. Okay. And this is also one of the other definition in other reference book. Okay. So both can be considered. Okay. So that is Martin diameter, right? Length of the bisect, which I have highlighted. Okay. And then we have a ferrite's diameter. In case of ferrite's diameter, this is a distance between two tangents. Okay. So this one is tangents. If you see here, the second here I have rounded here, right? So this image you definitely you can find in the Martin's book also. It is very nicely shown. Okay. And here also you can see. So that is a ferrite diameter, distance between two tangents. Okay. You know what is tangents, right? So distance between two tangents, parallel tangents. So that is known as ferrite's diameter. You have to remember that it's between two distance between parallel tangents. Then here we have used the word bisect. So you have to remember that word in your mind, because at the time of MCQ, they will give you a kind of a table kind of form, table form of MCQ, and they will just give you ask you to match it with the different definitions, and then you have to select the diameters, whether it's a projected or a Martin's diameter or a ferrite's diameter. Okay. Then we have a sieve diameter. Sieve diameter, it's simply that you sieve it, right? To the sieve shaker apparatus. We will see that also. Then we have a surface area diameter. Okay, so surface diameter or surface area diameter is the some for example, this is a irregular particle. Okay, and this is one sphere. So both have a equal surface area. Okay, both have I have written as A, area is A. So both have a equal surface area. So that is known as surface diameter or surface area diameter. Okay. That area, if you calculate for this particle and for this particle, although it's having an irregular shape, but area of the both sphere and this particle have a same area. So that is known as surface area diameter. Okay. Then we have a surface volume diameter, or it is also known as volume diameter. Okay. And in through which method we can get volume diameter? Through which method we can get volume diameter? Type your answer in chat box. Okay, so it's a diameter of a sphere having a same volume ratio. It means that we also can calculate the volume for these particles also, right? Through the density equation, rho is equals to m by v. We can also calculate the volume for both, right? So if that this both particle also have a same volume, so that is known as volume area diameter. Okay. Conductivity method, yes, but what is the actual name of the method? Or actual name? You are going right. I want the name of the, yes, Coulter counter. Yes, very good phase. Very good, very good. It's a Coulter counter method, right? Yes, very good. We will see that, but it's also important. Okay, through which method, which kind of diameter we find that, like for optical microscopy, we will get projected area diameter. Then for the Coulter counter, we get volume diameter. So that is very important. Surface area diameter you can get from the surface area measurement, which we have discussed in previous lecture, right? Air permeability method and adsorption method. Okay. So I think this both are same, or this is somewhat different, but in general, surface volume diameter and volume diameter, they are same. Volume diameter, as I have mentioned, that both have a same volume. And if they are talking about surface volume, but it's doesn't making sense. So both are almost similar. So you can consider volume diameter as a term that these two one irregular particle and sphere have a same volume. So they are known as volume diameter. Okay, remember this all definitions. It's very important. If you have any question, you can ask in chat box. Okay. So this we have discussed already, right? About the projected area diameter, then volume diameter, surface diameter. Then one more important term, which is Stokes diameter. What do you mean by Stokes diameter is that, for example, this is a spherical particle, whatever will compare it with the spherical particle always, right? Keep that in mind. Whatever we'll compare it, obviously our pharmaceutical API particles are not spherical in nature, but whatever we will compare it with the sphericals, because this one is a standard one, right? So this is a spherical particle and this is your irregular shape particle, but both have a same, you can say diameter. Okay, both have a same diameter and same volume. Okay, so if they have same diameter and same volume, they will travel through a same rate. Okay, through a same rate in the solution. Okay, if they are suspended, they will suspend with the same rate. Okay, that is known as sedimentation rate. So this both have a same diameter, and they are when they are suspended have a same diameter when they are suspended, and you can say sediment through sediment with the same rate. Okay, same sedimentation rate, then they are known as that diameter is known as Stokes diameter. Simply they are talking about that they are sediment with the same rate. Okay, the rate of sedimentation is equivalent, so that is known as Stokes diameter. Okay, as I have discussed here, it is written sedimentation rate. Okay, sedimentation rate is same. Okay, so that is known as Stokes diameter. Okay, and through which method we can get Stokes diameter? Through which method we can get Stokes diameter? Through which method? Yes, Anderson pipette. Very good. And you may get shocked that this for MCQ from the Anderson apparatus continuously in 2021, 2023, and sorry, in 2022 and 2023, continuously 3 years, the question has been asked from this topic, from this instrument, Anderson pipette method in different way. The answer was almost similar. but the way they have asked the question was somewhat different. Okay. So that is Anderson pipette method, through which we get the Stokes diameter. Now this is not a somewhat important part. Now this is very important. The different kind of a sieve size, right? This is also written in I think CVS Subramanian book of the pharmaceutical engineering part, right? It is written there also that what are the sieve size for the different particles. And one of the most important one is very fine. Very fine passes through the sieve size of 120 mesh. Okay. So this one is very important because in 2021 and 2023, this MCQ has been asked 2 times. Okay. So what is the CU size for very fine? Okay, fine, I think around 80 to 120. Okay, it is around, I think 80, right? Then moderately coarse, coarse and very coarse. It means that as you move downwards, the particle size will be lesser. So CU number would be higher. Okay. You can solve the MCQ like in that way. If you are not able to remember the number, so as you move down from coarse to fine, so particle size will decrease, and as particle size decrease, you require a increase the sieve number. You require a sieve with the more number of meshes or more number of apertures in that, right? So increase the sieve number. So remember this one, this concept. Okay. So as you increase the particles, in the particle size, or sorry, a decrease in the particle size, CU number will be increased. So remember in that way. So as you move from the very coarse to very fine, very coarse will be with the lowest CU number, and very fine will be with the highest CU number, which is 120. Okay. So remember that. And remember this concept. So you not need to remember the these numbers. Okay. And you are able to easily solve it without remembering that numbers. Okay. Just remember that as particle size decrease, the CU number will be increase. Now, as we have started somewhat this topic, that which kind of methods we can use for the particle size determination. So first one is optical microscopy, then sieving method. In sieving method, which apparatus we use? In sieving method, then sedimentation method. Which apparatus we use for the sieving method? Mechanical. No, it's a sieve shaker. Yes, mechanical sieve shaker. Yes, very good, Vivek. Yes, yes. Mechanical sieve shaker, right? So that is also one of the method for the particle size determination. Okay. Then optical microscope, sedimentation method. Sedimentation method, as we have discussed, that is Anderson apparatus. Yes, very good. What is the volume of Anderson apparatus? What is the volume of Anderson apparatus? Then Coulter counter method. Then laser light scattering. That is also known as dynamic light scattering. Method of determining then surface area. This we have discussed, right? In previous lecture, we have discussed this one. 550. Yes, it's I think around it's a 500 ml, right? It's a 500. Yeah, sorry. It's a 550. You are right. Nina Raju, you are right. Yes, it's a 550. Okay. So it's a 550 ml is the volume of the Anderson apparatus. Okay. So now we'll move with the methods one by one. So first one is optical microscopy. So in case of optical microscopy, the range in which we can measure the particle size is the 0.2 to 100 micrometer. Okay, it's a micrometer. 0.2 to 100 micrometer. Okay. And as I have told you that we use there is ocular micrometer in eyepiece. We fit ocular micrometer because we have to count the and measure the diameter of individual particles. Yes, pipette 10 ml. Yes, very good, Faiza Mehman. Yes, in case of Anderson apparatus, pipette is 10 ml, right? But first now focus here, okay? So eyepiece micrometer, in a case of eyepiece, we attach the ocular micrometer, and on this slide stage, here is the stage, right? Here in this portion, we put a stage micrometer, okay? So to determine the particle size of the individual particles. Okay, so we require ocular micrometer, which we fit in the eyepiece, and also the stage micrometer. Okay, these are very basic concepts, but you have to remember because this can also be asked as a MCQ. Okay, because directly you cannot measure the particle size of the individual particle through the optical microscopy. You have to attach the ocular micrometer in eyepiece and stage micrometer at the stage, and then you can measure it. Okay. Then the different other methods which we use the SAME and TAM. Okay. Scanning electron microscope and the transmission electron microscope. What is the difference in principle of scanning electron microscope and transmission electron microscope? Both are electron microscope. So what is the difference? What is the difference? Okay, I will tell. So in case of scanning electron microscope, what we get is a electrons which are, you can say, scattered from the surface. Okay, so generally that's why it is also known as surface scanning electron microscope. So scanning electron microscope just scan the surface. Okay, so if you want to know about the surface morphology of any particle, so or shape of the particle which is in the nanometer range, okay, or also in the micrometer range, so you can measure that or measure their surface. Okay, so it scan the surface and provide the surface image, right? And TAM provide the inside structure. Yes, same give 3D images. Yes. So in case of TAM, we will get a idea about internal structure also, right? So that is the main difference. And also in case of transmission electron microscopy, in case as it is name itself indicate that we measure the transmitted electron which are scattered from the surface. Okay, and here we measure the transmitted electrons. Okay, through the specimen. It means that electron get transmitted through the specimen, and that electron we will measure. Okay, so in transmission electron microscopy, we will get idea about the internal structure, while in case of scanning electron microscopy, we will get idea about the surface only, right? For internal structure, we have to go for the transmission electron microscopy, right? For example, on a part, if you want to see the particle surface, you can use SAM. What is inside the particle? For that, you have to do scanning electron microscopy. Okay, this is also very important, right? Basic concept. What is the difference between these two, and for which you and what is their use? Okay. This is the image. This is not required to study in deep, but this is what the you can say image of the schematic and as well as the original image of the transmission electron microscope. And this is what this is a image of nanoparticle. And this side one is this one side is nanoparticle, on the right side, and on the left side, they are liposomes. Okay, so how they are that are in the nanometer range. So this is the image. Now this is the CU method as we have started, and which kind of distribution we'll get, whether it's a number distribution or weight distribution in case of CU method. Why I'm asking spontaneous questions, just to give you a insights, because at the time of exam you have to do the everything at a time, right? Yes, very good. You have to do everything in a 3 hours. Okay, so you have to ready for everything. You not have to give it individually, that you have to give everything at a time. So your mind must be ready for the things that you are also giving. You are also ready with the that some tricky question asked to you, right? Because you have a mix of the all subjects. Okay, so ready with that also. So in case of CU method, as you have told, we get the weight distribution, right? And up to which micrometer size we can measure is 45 micrometer, and maximum we can measure is 1,000 micrometer. Okay, and this is what the CU shaker apparatus is. You have to remember what kind of distribution we get, and also what is the name of the apparatus. Okay. And principle of measurement is very simple, as it is written that it is shaker, right? So it's a sieve shaker. So it shake the entire instrument, is just kind of agitation will be there in entire instrument. So particle will just move because of the agitation through the different sieves, and they will get separated according to their particle size. Okay, so that is what written in this slide. Now, this is very important. This is what we have just discussed few minutes ago about the Anderson apparatus. So this is Anderson apparatus, or also known as Anderson pipette. Okay. And as we have discussed, the volume of the entire one is around 550 ml. And the volume of this pipette inside this apparatus is around, as someone has told, it's about 10 ml, right? And also the important part is that which kind of diameter we will get from this instrument is the Stokes diameter. Okay, we get the idea about the Stokes diameter, and which kind of distribution we will get from this instrument, which kind of distribution it will provide. Type your answer in chat box. As we have discussed that it is based on the sedimentation, whether it will be weight distribution or number distribution. Weight distribution or number distribution in case of sedimentation method, the Anderson apparatus. It will be weight distribution. Okay, because whatever powder will be, yes, Roho, very good. Yes, Gayatri, very good. So it will be weight distribution. Why? Because after sedimentation, there will be a particular weight you will get. Okay. After each time point, you will get some weight here at the bottom. So that's why it's a weight distribution. Some weight of the powder you will get, right, in a particular diameter range. So that's why it's a weight distribution. Okay. Then we'll see some examples where we in the methods where we get the number distribution, like optical microscopy, transmission electron microscopy. We will get the number distribution where we are measuring the number of particles, number of particle in a particular diameter range. And there is here in weight distribution, we are talking about a weight of a particles, or a number, or you can say a weight of a particles with the specific diameter. 30 into 10 in for example, in 10 to 20 micrometer, there is a powder weight of the particles is around 10 grams, or that is what weight distribution mean by. Okay. So this is very important. Anderson apparatus. And this is the very important equation because I think this was in the second shift or first shift of GPAT 2023. Which equation is this one? Which equation is this one? Just we have discussed few minutes ago. Yes, Stokes equation. Very good. Yes. So it's a Stokes equation, right? From this Stokes equation, which kind of information we can get is that we can get the idea about the sedimentation rate. That is V. Okay, sedimentation rate. And we also get the idea about its, as we have discussed, Stokes diameter. Okay, and this is very important equation. This both are very similar equations, just somewhat different. And there is one more equation where it is written like a 9 is written, right? Where there is a no square root, but it is 2 into 9. So 2 into 9. So it's just a mathematical conversion, right? Somewhere it is 9 also written, but they also added in multiplication 2. Okay, so they both equations are similar. Okay, this one and that one where 9 is written in numerator. Okay, so remember that both. Okay, and this was in, I think, GPAT 2020 first or second shift, I think, right? So this is very important. Stokes equation, as where I have told, rate of settling, that is rate of sedimentation. Then H is a distance, like for in case of Anderson apparatus. So for if the particle is traveling from here to here, so this is the height, okay, or the distance of the particle which particle travels. Okay, then the Stokes diameter, then the density of the fluid which we have, field and density of the particle. Okay, N is a viscosity of the medium, and G is a acceleration due to gravity, that is gravity constant, right? Now, why I am discussing these terms also, because they will ask you the question from this also, that what is this? They will give you an equation and they will ask you these terms, that what is the meaning, what is the DST, what is the rho s, rho g, rho zero, what do you mean by V? Or they will ask you equation as well as these terms also. Okay, because question from the Stokes diameter also, there are many other times they ask the question from the Stokes diameter also. Okay, so remember this Stokes equation and Stokes diameter, as we have discussed the definition of Stokes diameter, right? That is similar particle, spherical particle and irregular particle undergo having a same sedimentation rate. Then this is also a cascade impactor. The most important point in case of cascade impactor you have to remember is it is also used for the determination of particle size, but for the DPIs. Okay, for the dry powder inhalers, yes, or aerosols, yes, aerosols, and specifically in that there is also DPI comes, right? There is also part of DPIs are also covered under that, and aerosols also, right? So we can measure the particle size distribution of the DPI and aerosols in case of cascade impactor, right? In aerosols there is a different three terms of the MDIs, that is meter dose inhalers, then dry powder inhalers, and then the nebulizers. Mid MDI is also known as aerosols. Okay, and also in category of aerosols is a broad term. In DPI also can be covered. But remember that for which kind of dosage form this cascade impactor is used for the particle size measurement. So that is dry powder inhalers. Okay, and also you can mention the aerosol also. Okay, so this is very important. Then different techniques for the measurement of particle size is the X-ray sedimentation, laser light scattering, electron sensing zone, and surface area we have already discussed. Okay, so remember the name of the methods only. Okay, it may be asked as a MCQ that what are the different other methods, or which of the following are the other method measurement techniques for the particle size analysis, okay, or measurement. So you have to remember these methods. Okay, that is electron sensing zone, then laser light scattering, and the particle size by surface area, and laser light scattering also known as dynamic light scattering. Okay, dynamic light scattering. And this dynamic light scattering work on the principle of Brownian motion. Brownian motion we will discuss in the colloidal dispersion chapter also in the upcoming slides. Okay, so that is Brownian motion. Kind of a random movement of the particle in the liquid, that is Brownian motion. Okay, so that is the through which we can measure the particle size by laser light scattering. Okay, because that moving particle scatter the light. Okay, now important thing is about the Coulter counter method. First very important thing is about the Coulter counter method is the we get the volume diameter. Okay, in case of Coulter counter method, and it is also known as electron sensing zone method, as we have seen in the previous slide, right? So that is also known as Coulter counter method is also known as sensing zone method or electron stream sensing zone method. Okay, and the important thing is the volume area diameter we get, and also that this method is based on the electrical resistance measurement, right? So it will generally measure the electrical resistance, as the in this Coulter counter instrument there is a one orifice. From orifice the particle will pass down, and as particle will pass down from the orifice and move in the other in out from this orifice, so the solution which is filled in this tube, this will be the volume of that you can say particle will be displaced from that solution as it is move out from this orifice. So there is a change in the resistance of this entire solution. Okay, and which is correlated with the voltage and also correlated with the measurement of the particle size of the particle, that how much volume it is displacing from this solution. Okay, so that is the simple principle based on the electrical resistance measurement, which they are correlating with the voltage. Okay, so remember this electrical resistance and correlation between the voltage. Okay, and then they are correlating it with the measurement volume area volume diameter. So this is what I am talking about. This is the orifice. Okay, this is the orifice. As you know, right, that particles, smaller particles have a charge. Okay, and that's why they will move from this orifice because of the electrical you can say kind of a electrical attraction. Okay, and then because of that they will move towards the opposite electrode, right? And because of that they will displace their volume from this out they displace out from this orifice, and uh, they will displace their volume in into this tube. Okay, and that will be measured as its volume area diameter, right? And that's why we have told it as a volume area diameter, because we will measure it through the how much volume it is displacing, okay, in that orifice test tube. Okay, and this is also a schematic image of the Coulter counter instrument. Okay, so here is a electrolyte solution and particle. Okay, somewhat to make particle chargeable, it also we also add electrolyte solution. Okay, as you know that as we add electrolytes, it will also help in the completion of circuit. Okay, this is what the orifice is. From this orifice the particles will come into the another beaker, where it is also contains solution, and this test tube also contains solution or sample solution. Okay, so the instrument will measure how much volume is displaced from this test tube. Okay, so remember this concept. The principle is very important, as I have discussed the resistance, and then it correlate it with the voltage. Okay, remember the principle also. So as I have discussed the principle, it is written here. Volume of the electrolyte fluid which is displaced by the orifice, presence of the particle which can cause change in the electrical resistance between two electrode, and which is proportional to the volume of particle. Okay, which I have discussed already. Then as I have discussed about the laser light scattering method, which is based on the Brownian movement. Okay, and simply based on the scattering of the light, that this is your particle. These are the different rays are you can say bombarded on the particle, and then this particle, because of that, this light will be scattered out in different directions, and this is known as dynamic light scattering. Okay, and we will measure the intensity of the scattered light, and based on that we'll get the idea about the particle size of this particle. Okay, and the standard instrument which is based on the DLS method is the zeta sizer. Okay, for the measurement of the nanoparticle size, right? Nanoparticle size we can measure through zeta sizer, and also the measurement of the zeta potential. Okay, zeta potential we will see in the colloidal dispersion chapter, which is in upcoming slides. We will see that also. Okay. So this is what I was talking about, right? And these are very important terms: diffraction, refraction, and absorption. Okay. So as you can see here in this image, remember these definitions, because in just in this year GPAT 2023 there is a question from, I think, a reflection or refraction. They have asked the question from this definition. Okay, so what is diffraction is that diffraction is just this red arrow, right? This one, this is diffraction. So simply a particle is here, so when light comes, its direction is changed. Okay, so change in direction, that is diffraction. Okay, change in direction, that is diffraction. Then we have a reflection. So remember that reflection occurs at a 90 angle. Okay, and then there is a refraction, where in case of refraction it will move from the particle. As you can see, it is moved through the particle, and then its direction is get changed, right? This surface of the particle. Okay, so that is the difference between refraction and diffraction. Refraction will be through the particle, and diffraction will be from the surface of the particle. Okay, and reflected way. Okay, reflected way, if you see, reflected way will be at the angle of 90. Okay, so that is the reflection. And absorption means simply that your particle will absorb the light. Okay, the light which you have transmitted on your particle, it will not come out. Okay, it will get absorbed into that particle. So that is known as absorption. Okay, so remember the definitions. What is diffraction? That is change in direction. Okay, reflection, it means that particle from light will not uh, cross the particle, but it will just come back on the path, same path. And as I have discussed, that it is based on the principle of Brownian movement. Okay, this dynamic light scattering and light scattering method, it is based on the Brownian movement measurement. Okay. This one is not important for you. Yeah, different densities of the particle, right? The most important one are the true density, then granular density and bulk density. In granular density, which kind of void space which kind of pores we will cover? Whether it will be intraparticulate or interparticulate for the measurement of granular density? Type your answer in chat box. Intra. Intra, yes, very good, very good. Nina Raju, very good. Yes, it's a intra, right? Yes, very good. So it's a intra. Okay. And in case of true density, whether we cover interparticular or intraparticular, in case of true density, whether in case of true density, what we will cover? Intra or inter? Inter. In case of true density, we will not cover the void space. Okay. This question I have asked you to trick you. Again, I am repeating that which kind of void space we will cover for the measurement of true density. We will not cover the inter also, and we will not cover the intra also, because we want true density, right? It means we are excluding the void space. Okay, we are excluding the void space for the measurement of particle size. Okay, so we are excluding the void space for the measurement of the particle size. So that's why we get the true density. Okay, so we will exclude both intraparticular void space and interparticular void space. Okay, both will not covered here in case of true density. And for the true density measurement, we use helium cyanometer. Okay, which is a gas displacement method. Okay, then we have a bulk density. In bulk density, we will cover both. We consider both inter and intra particulate void space, both we will cover in case of bulk density. Okay. Then we have a tap density. Okay, tap density means simply we tap the powder into the measure the powder, take the powder into the cylinder, that is measuring cylinder. We'll put that measuring cylinder on a tapping apparatus, right, which taps the cylinder, and after some number of tappings, we'll get a density, and that density will be tap density. Okay, so that is, it's because of tapping. Because of tapping, it will exclude the intermolecular interparticular space, right? Interparticular void space will be excluded or removed, right, because of the tapping. So that density what we get is tapped density. Okay. Then we have a granular density, as we have discussed this in previous lecture also. that granular density, we will include the intra particular void space. Okay, and it is measured by the liquid permeability method or liquid displacement method. Sorry, liquid displacement method, which is mercury displacement method. Okay, which is very important. Remember this. Okay, and this is generally used for the granule density measurement, and that's why it's known as granular density. Okay, remember this. Whatever I have discussed till all can be asked as a MCQ. And this is also very important. Porosity. Porosity is simply a bulk volume minus true volume, which is also known as void volume. Void volume, V as volume, void volume upon the bulk volume. Okay. Into 100. This is also a one formula, because if you just solve it mathematically, so this will get goes into denominator. So that will be bulk minus true volume, that is known as void volume, and also upon bulk volume. So that is into 100, you will get porosity. Okay. So this is the porosity formula. Okay, remember this also. Formula for the porosity, that is void volume upon bulk volume, or bulk volume minus true volume upon bulk volume into 100. Now also I have asked this question in previous lecture, that what will be the ratio of the volume to surface area, right? So that is the 6, right? Surface area to volume ratio of a particle, if it is 6, then that particle will be considered as a spherical particle. Okay. So this I have already told. Then flow property, we will measure angle of repose. We have also discussed the angle of repose method, measurement of angle of repose, different methods. That is a static and dynamic angle of repose, right? How we can measure that, we also have discussed. So this is about this chapter of the micromeritics. Then now we will start with the rheology chapter, right? And in case of rheology, we will see some different types of flows, their example, and then different methods for the viscosity measurement. And then we will move towards the colloidal dispersion, where we will see gold number. What is gold number? Then what kind of what is lyophilic, lyophobic, and association colloids, right? And what are the different properties of colloid? Okay, so that we will discuss in next 1 hour. Okay, and then we will finish our lecture. For a few minutes, I'm just stop my screen. So I will just share the PPT of rheology. Okay. Is my screen visible to everyone? Okay, okay. Thank you. Thank you. So rheology is simply what is rheology is the flow of fluid, right? You can say it, flow of measurement of the flow of fluid, or a flow of solid also can be considered as a rheology. So that is rheology. Okay, what we mean by the term rheology. Okay, and we will directly discuss, directly jumps on the different flows, which is very important, right? The MCQ, from which part the MCQ comes. Okay, so this is the Newtonian system. Now, what is Newtonian system? Where the rate of shear is directly proportional to the shearing stress. Okay, where the rate of shear is directly proportional to the shearing stress, that is known as Newtonian system. Okay, so this F is your shearing stress, and this dV by dr, this is your rate of shear. If both are proportional to each other, as you giving a stress, also rate of shear is also increasing proportionally. So that is known as Newtonian system. And in Newtonian system, you will see graph like this, right? A straight graph between the shearing stress, that is F I have written here, and the rate of shear, also not written as dV by dt. Okay, so rate of shear and shearing stress are directly proportional. Remember this graphs also. Okay, they are also asking the graph based MCQs. They give you simply a graph, and they will tell you to identify the which kind of system this is, whether it's a Newtonian, non-Newtonian, plastic, pseudoplastic, or a dilatant. Okay, what are the different examples of Newtonian systems? Different example of Newtonian system. Type your answer in chat box. Water, yes. Other examples, very important. They can ask as MCQ. Water, ethanol, other. No. Flocculated suspension will not cover the in the Newtonian system. Yes, very good. It's a chloroform and glycerol, right? It's a chloroform and glycerol. It's a chloroform and glycerol, right? So, very good, very good. Yes. Benzene, castor oil. Yes, these all are the Newtonian system. It means they flow easily, right? And also their viscosity is also you can say same. Okay, their viscosity will also not change. This kind of graph also can be possible. That it will be against viscosity versus, I have written it here, viscosity versus the shearing stress. I have written it as a SS. Okay, shearing stress. So this will be constant. Okay, straight line will be there. So this is also known as viscogram. In the previous year one, which I have written it, that is of shearing stress versus rate of shear, that is known as rheogram. Okay, this is also basic importance. Remember this also. Okay, whether they are asking rheogram, viscogram, viscosity versus shearing stress, or a shearing stress versus rate of shear. Okay, so this is of the new for the Newtonian system itself, but it is of the viscosity versus shearing stress. So this is also will be straight line. Okay. So this is the equation, right? So this is your shearing stress, that is F. Okay, or in some books they have written it as a P is equals to F dash by A. They are considering it is a kind of a pressure or a stress you are applying at one side, right? And that is dV by dr is your shearing stress. Okay, sorry, rate of shear, RS. That is written as rate of shear. Okay, and this is what I am talking about. This one is rheogram. This G is your rate of shear. Okay, different they have terms given, but the meaning is same. Okay, that is rate of shear, and this one is shearing stress. Okay, and this is also one equation, that is N is equals to F by G. Okay, this one is G. Okay, and this one is your F. So F is equals to F dash by A, and G is equals to dV by dr, that is your rate of shear. Okay, now as we have discussed the examples also, now we move towards the non-Newtonian system. What do you mean by non-Newtonian systems? What do you mean by non-Newtonian systems? What do you mean by non-Newtonian systems? Where the rate of shear is not directly proportional to shearing stress. Right? No, 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 no. Gayatri Bevani. No, beta, it's not a true definition. The true definition is that the rate of shear is not directly proportional to shearing stress. That is the true definition. It doesn't follow Newtonian law. No. Okay, remember this definition. Don't tick this also. Okay, it's a very misconception with the Newton's also law also. Okay, sometimes students consider it as a Newton's law, but it's very somewhat different from that. Okay, it's regarding the flow. Okay, so it's a flow. The rate of shear is not directly proportional to shearing stress. So that is known as non-Newtonian system, and if it is proportional, then that is known as Newtonian. Okay. Then one more important term is the kinematic viscosity, which is viscosity by density. Okay, and you can say the unit for that is stocks and centistocks, because this MCQ has been asked 2 times. Okay, in the GPAT 2019 and also in GPAT 2022. Okay, 2 times this term has asked what is the kinematic viscosity and what is its unit. Okay, so it is viscosity by density. And one more important thing is the reciprocal of the viscosity is known as fluidity. Okay, viscosity is simply resistant to flow, right? That is resistance to flow, that is viscosity, and fluidity is opposite of the viscosity, right? So it's a reciprocal of viscosity. Remember each and every term which I am discussing. Okay, everything can be asked as an MCQ. So this is the examples of the Newtonian liquids which you all have give: olive oil, castor oil, then chloroform, ethanol, glycerine. Okay. This is also an important equation, that is Arrhenius equation, which states the relation between the temperature and viscosity. Okay, that is viscosity is equals to A e raised to EV by RT. Okay, that is Arrhenius equation, which express the relationship between the viscosity and temperature. And this question was in GPAT 2023. Okay, so remember this, that which equation will state the relation between the temperature and viscosity. So that is the Arrhenius equation. Okay. Now non-Newtonian systems, right? In non-Newtonian system, as I have discussed, that non-Newtonian, in case of non-Newtonian system, the rate of shear will not be proportional to shearing stress. That is known as non-Newtonian systems. And in non-Newtonian system, they are divided into 3 different types, that is plastic, pseudoplastic, and dilatant. Okay. And what are the examples of non-Newtonian systems, right? So that is the heterogeneous dispersions. Heterogeneous, it means a solid dispersed in particular liquid. That is, the examples are the emulsion, suspension, and ointments are the heterogeneous dispersions. Okay. So emulsion and suspension and ointments, they show this non-Newtonian behavior. Okay. And why they are non-Newtonian? Because their viscosity changes with the time. And that's why also we can say its rate of shear also changes with the time. Okay, it's not constant. If it is constant, then we consider it as a Newtonian system. Okay, but it is not constant, and that's why we consider it as a non-Newtonian system, because its rate of shear will change with the shearing stress and its viscosity also change. Okay, and now we move for the plastic flow. Okay, as I have told you. Now plastic flow. This is very important graph. Remember every graph for every system, for Newtonian, non-Newtonian, dilatant and plastic also. Okay. So in case of plastic flow, what you have to see here is the rate of all graphs will be, this one is rheogram, right? As I have discussed, rate of shear versus shearing stress will be rheogram. And if it is for the viscosity, then it's known as viscogram. Okay. So here the rate of shear and the shearing stress is not directly proportional, right? Here you can see it's not directly straightward line. Okay. But rather than straight line, it's starting flow after some point. After some point, right? So, and that point is known as yield value. It means that after a certain amount of pressure you will apply, then and then that fluid will move, and that is known as yield value. Okay, that pressure value where it start flowing. So that is known as yield value. Okay. And also the viscosity which we get from the plastic systems, that viscosity is known as plastic viscosity. Just to differentiate term, it is known as plastic viscosity. And the reciprocal of the plastic viscosity is known as mobility. Okay. So remember this. And here you can see that it's not, and also this graph is not passed from the origin. All other graphs will pass from the origin, but this graph is not passed from the origin. Okay. So remember this also. Okay. And that is plastic flow. And which kind of systems will show this plastic flow behavior? That is flocculated suspension and Bingham bodies. Okay. There is sometimes a misconception that they consider Bingham bodies in the pseudoplastic flow, but it is not it doesn't show pseudoplastic flow, it shows the plastic flow. Bingham bodies show plastic flow and also the flocculated suspension. Okay. This is the examples which I am talking about. That is the Bingham bodies, and also the reciprocal of the plastic viscosity, that is mobility. Okay. And as we have discussed the yield value, and also note down the flocculated suspension will also show the plastic flow. Okay, flocculated suspension, because deflocculated one show the deflocculated suspension will show dilatant flow. Okay, they will show the dilatant flow. And this is the formula to find the plastic viscosity. Remember this all formulas also, as in case of Newtonian, we have seen that it is F n is equals to, that is eta is equals to F by G for Newtonian. Here for plastic flow, plastic viscosity, which is denoted as U, is equals to F minus F dash by G. Okay, and this F is your yield value. Okay. The entire, if you see the formula is same, just they have minus out the yield value, as it's not start flowing directly. We require some amount of force need to apply first, and then it will start flowing. Okay, and that's why its graph also not passing from the origin. Then we have a pseudoplastic systems. In case of pseudoplastic systems, what happens that its viscosity decreases with the time. Okay, their viscosity decreases with the time. So that is known as plastic flow system. Okay, their viscosity decreases with the time. So if you see their viscogram, it will be like this. This is the viscosity and this is the shearing stress. Okay. So as you increase the shearing stress, their viscosity will get reduced. Okay. Their viscosity will get decreased, and that is known as pseudoplastic flow and pseudoplastic system. And also the example of this systems are the natural polymer solutions. As I also mentioned this in previous class also, right? Tragacan, then sodium alginate, cellulosic polymer, sodium CMC. Okay, this all cover under the then acacia also. This all will cover under the pseudoplastic systems. Okay, and they are also known as shear thinning system, right? Shear thinning, because their viscosity will get reduced with the increase in the rate of shear. Okay, and that's why they are known as shear thinning system. Okay, they are also known as shear thinning system. In case of pseudoplastic flow systems, this one is a rheogram. The previous one which I have shown you in slide, that one was of is a viscogram, right? And this one is a rheogram. And as you can see, its rate, as you increase in the rate of shear, its shearing stress is also increasing, but it's not exponential, right? It's increasing slowly. Okay, it's not exponential. Exponential means a straight line, that it's directly increasing, but it's not increasing in a straight way, straight manner, right? Okay, as you increase the rate of shearing rate of shearing stress, the rate of shear is also increasing, but not directly. Okay, it's increasing in a indirect manner. Okay, or you can say not a straight way, not an exponential way. So this is the rheogram. Previous one was the viscogram. Okay, remember all viscograms and rheograms, very important. And this is very important equation which from which I have asked you one MCQ, that what will be the n value of n for the uh, pseudoplastic system and what will be n for the dilatant. So n value will be greater than 1 for the pseudoplastic and n value will be less than 1 for the dilatant system. Okay. For the dilatant, value of n will be less than 1. Okay, remember this also. Value of n will be less than 1 for the dilatant system. Okay, and this is very similar equation, but as they are not you can say true, or you can say they are not Newtonian system, so we have included a one n term. Okay, and that n value will be greater than 1 for the pseudoplastic and for less than 1 for the plastic system. Now we'll see different one example of the dilatant system, and then we'll move for the colloidal uh, particle and colloidal dispersion. Okay. Then dilatant flow. These systems are also known as shear thickening system. Okay. They are also known as shear thickening system. It means that as you increase the rate of shearing stress, as you increase shearing stress, their viscosity will also get increased. Okay, the viscosity is also get increased. As you increase the shearing stress, the viscosity also get increase. Okay, so these are known as shear thickening system, and it will be observed in the deflocculated suspension. Flocculated suspension will be for the plastic system, and this will be for dilatant, that is deflocculated, and also they contain 50% solid or greater. That kind of solutions will show the dilatant flow, and the example is deflocculated suspension, as we have discussed this MCQ in previous lecture also. Okay. In this question was in the GPAT 2023. Okay, and this question was in GPAT 2023. Now, which kind of methods are available to measure the viscosity? Type your answer in chat box. Now it's your turn to give answer the questions. What are the different methods available? Capillary, and there are two methods, right, for the measurement of particles size. Yes, so two methods are single point measurement and multi-point measurement, right? Single point measurement and multi-point measurement. So in case of single point measurement, these methods will be used for the Newtonian system, right? These methods will be used for the Newtonian system. While in case of multi-point measurement, this multi-point measurement methods will be used for the non-Newtonian systems. Okay, like for dilatant, pseudoplastic, plastic. Okay, for non-Newtonian. And this one would be for the Newtonian systems. Okay. So this is the first important thing that you have to remember. And then in single point measurement, the capillary viscometer, that is Oswald viscometer, right? So that Oswald viscometer and falling sphere viscometer will be covered under the single point measurement method. Okay, and that's falling sphere viscometer is also known as Hoppler viscometer. Okay, is also known as Hoppler viscometer. And this question, I think, is in around 2018 or 2019. Okay, that is also falling sphere viscometer, based on the falling sphere viscometer. The other name of falling sphere viscometer is the Hoppler viscometer. Okay. And in case of multi-point measurement, we have, yes, rotational method, that is cup and bob viscometer, then Brookfield viscometer, that will be covered in that. And other types are the Sherale and non-Sherale type. Can you tell me the examples of Sherale type and non-Sherale type, or Cott type? Sherale type and Cott type, what are their examples? What are their examples? Sherale type and Cott type. McMichael, yes, very good. It covers under the Sherale type or Cott type. It's a Sherale type, right? McMichael viscometer. And the Cott type will be cup and bob viscometer. From C, you can remember the cup, right? Cott type also having a starting letter C. And in case of cup and bob viscometer, also C. So from that, you can remember it as a cup and bob viscometer will be covered in that Cott type. And in case of Sherale type, McMichael viscometer, and also Brookfield viscometer also covered under the Sherale type. Okay. Brookfield viscometer also covered under the Sherale type. Okay. So these are the different methods. Then there is one more, cone and plate viscometer. Okay, cone and plate viscometer, which is also based on the rotational method. So remember that for the Newtonian system measurement, only Oswald and the Oswald and capillary Oswald viscometer, which is capillary viscometer, and falling sphere viscometer, only can be considered for the measurement of the single point measurement for the Newtonian fluids, while other are multi points, so they can be used for the Newtonian as well as non-Newtonians. Okay, so this is very important methods. Okay, there are very few methods, so that's why I haven't included in slides, and you guys have answered it very nicely. Okay, so remember these methods also very important. Okay. Now we will move towards the colloidal dispersion, and before moving to colloidal dispersion, I want to ask you some more two questions. That is, what do you mean by the rheopaxy, and what do you mean by the thixotropy and antithixotropy? Type your answer in chat box. Type your answer in chat box. What is rheopaxy? Gel to gel sol gel. Gel sol gel will be covered in thixotropy. Very good, Gayatri Bhavani. Yes. And it will be faster or slower? Reconversion will be faster or slower? Recovery will be faster or slower? It will be slower, right? Yes. If it is slower, then thixotropic. Okay. Yes. And what will be the reverse will be? The reverse will be anti-thixotropy. That is negative thixotropy, right? That is negative thixotropy. Okay. Negative thixotropy, it is sol gel sol conversion, right? Yes, very good. Okay. And that the rheopaxy, what will be the in case of rheopaxy? Gel to gel sol gel, right? Gel sol gel conversion, but it will the recovery will be faster. Slight agitations, this kind of terms you may have heard. And this MCQ has been asked previously in the GPAT 2021. Okay. In GPAT 2021, they have asked the term rheopaxy. Okay, so that is faster recovery, right? Through slight agitation or slight disturbance, they will get recover. Okay. And sol gel sol means a solution converted to gel, and gel again converted back to the sol. Okay. So remember this concept also very important. Okay, on it 2 to 3 times also MCQ has been asked from this concept also. Okay, now we will move towards the last portion of the today's lecture, which is colloidal dispersion. And for that, I will just share my screen again. Okay. Is my screen visible to everyone? Is my screen visible to everyone? Okay, okay, thank you. Now, last topic for today's lecture is the colloidal dispersion. Now, the first important thing is what can be considered as a colloidal. So, the particle size 1 to 1000 nanometer. This will be considered as a colloidal range. Okay. Particle size 1 to 1000 nanometer. That will be considered as a colloidal range. Okay. Then there is a molecular dispersions also. This one is colloidal dispersion. The molecular dispersions will be particle size will be less than 1 nanometer. Okay. Less than 1 nanometer. Okay. So that is known as molecular dispersion. And if the particle size is greater than 1000 nanometer or greater than 1 micrometer, both are similar. Okay. 1 micrometer or 1000 nanometer. Okay. So this is known as a coarse dispersion. Remember this basic difference between these three can be asked as an MCQ or in the form of table. They will ask you the particle size range. What will be the particle size range? And in some books also they have written it 1 to 0.5 micrometer for the colloidal, but the actual correct will be the 1 to 1000 nanometer or 1 to 1 to 1 0.1 to 1 micrometer. Okay, so it is very important to remember the actual range is 1 to 1000 nanometer, but in some books this value is written, so remember this value. Okay, 1 to 1000 nanometer. Okay, so that is colloidal range. And can you tell me our blood is which kind of dispersion, whether it's a colloidal, coarse, molecular, or a colloidal? Our blood is only coarse dispersion, only coarse. I am asking whether it's colloidal, coarse, molecular, or three, or all of three. Colloidal and coarse. I think you guys have to read the reference books thoroughly, right? Because our blood is contain all three dispersions. Again, I am repeating, it contains molecular level dispersion also, molecular level dispersions also, colloidal dispersion also, and the coarse dispersion also. Molecular dispersion, the nutrients which we are taking, nutrients and oxygen, they will dissolve right into the blood plasma. It contain water also, right, or plasma, so that will dissolve in that. Okay, so that is from the molecular level dispersion. Then the proteins, plasma proteins, that plasma proteins will form a colloidal dispersion. Okay, and your RBCs will form a coarse dispersion. Okay, so that's why our blood is a contain all three dispersion systems, which is molecular, coarse, and colloidal and coarse dispersion. Okay, so this can be asked as an MCQ, that what is which kind of dispersion system our blood contains. So it will be all of three. Okay, as I have mentioned the examples, that nutrients are the form molecular dispersion, plasma proteins will form the colloidal dispersion, and the coarse dispersion will be formed by your RBCs and the WBCs. They will form the coarse dispersion. Okay, now which are the types of the colloids? Right, now colloidal solutions have different types. Colloidal dispersion, sorry, not solution, colloidal dispersion. Which kind of what are the three types? I will give you a hint. What are the three types of colloidal dispersion? What are the three types? Answer fast. Lyophilic, yes. Other one, other two. Lyophilic is written in this slide. Yes, lyophobic, and one more. Association. Very good, very good. Yes. So these are the three types, right? Lyophilic, it means simply solvent loving. Lyo means solvent. Okay. Lyo means solvent. Okay. So it is important. Philic means loving. So it's a lyophilic colloids. Okay. And these colloids are easy to prepare, easiest to prepare. That is lyophilic colloids. Okay, and the lyophobic colloids are the hardest one to form. Okay, and to stabilize. Lyophobic colloids are hardest one to form and to stabilize them. Okay, the most important thing is that in case of lyophobic colloid, as they are solvent loving, so solvent will form a film around your particle or colloidal particle, and that film is known as a solvent sheath. What is it known as? Solvent sheath, which is not present in case of lyophobic colloid, as they are not, as they are solvent hating. Okay, as they are solvent hating, so that's why the solvent sheath is absent in case of the lyophobic colloid, while it is present in case of the lyophilic colloids. Okay. And what are the examples of the lyophilic colloid? Is the acacia, gelatin, rubber, polystyrene, but this is in the organic solvent. Okay. Obviously, rubber is if you consider it hydro in case in terms of water as a solvent, they are lyophobic. But for the organic solvent, if you disperse them in organic solvent, they are act as a lyophilic colloids. Okay. So remember this also, as here written hydrophilic and lipophilic. Okay, hydrophilic, it means that they are water loving. Although they are lyophilic, and particular solvent we are considering water. Okay, and if it's organic solvent, then examples are rubber and the polystyrene. Okay, remember this also, an organic solvent, benzene and ethyl methyl ketone. Okay, as a solvent. Now lyophobic colloids. Lyophobic colloids, as its name indicates, they are solvent hating. It means that they not get easily dispersed into their solvent, right? Into their dispersing medium. They are not get easily dispersed. And also after dispersion, they get destabilized. It means that your colloidal particle will convert into the bigger particle through the particle growth. Okay, because of the lesser affinity towards the solvent. Okay, and also that's why they are thermodynamically unstable, while the previous one, which one is lyophilic, they are thermodynamically stable. Okay, so this is also an important differences you have to note down. Solvent sheath is present or not, then whether it's thermodynamically stable or unstable. Okay, remember this all the terms. Okay, and also they contain charge on their surface. In case of lyophobic colloids, they contain charge. Okay, and the example of, can you give me a most common example of negatively charged colloid? Common example of negatively charged colloid? Most common example? It's a gold, right? Colloid of the gold. Okay, that is lyophobic colloid and it is negatively charged. Okay, remember this. Now, as I have also told you that it is not easy to prepare lyophobic colloids. Okay, lyophilic colloids can be easily formed just by simple dispersion of your colloidal particle into a solvent. But lyophilic phobic colloids cannot be formed easily. And for that, you require a special method. There are two types of method, dispersion method and condensation method. Remember these methods also. Milling and grinding process. In milling process, which kind of mill we can use? In milling process, type your answer in chat box. Which kind of mill we can use? And in case of dispersion method, what do you mean by dispersion method? Is that we decrease the particle size in colloidal range, right? For example, this one is micro particle. So we reduce the size of the this particle into nanometer range, the 1 to 1000 nanometer range. Okay, and this is known as dispersion method. Okay, type your answer in chat box. Colloidal mill, right? Yes, yes. Muralidhar Nalwade, yes, it's a colloidal mill, right? We use colloidal mill in case of milling and grinding process. Peptization, okay, we also include same concept. Okay, in case of peptization, we reduce the particle size in nanometer range. Electric arc method and the ultrasonic treatment. Here we use the ultrasound. And how ultrasound will reduce the particle size? How ultrasound reduce the particle size? By the cavitation. Okay, by the cavitation. Okay, remember this. They generate heat also, and also they do then the cavitation. Okay, the principle is cavitation. Okay, and we use the ultrasound waves for the reduction in particle size. So these are the dispersion methods. And then in case of condensation method, there is a one method, that is anti-solvent method. That is addition of non-solvent, that is also known as anti-solvent, in which your colloid is not stable, or your the molecule, first you will dissolve your colloidal particles into a solvent, and then you add a solvent in which they are not dissolved, and that solvent is known as anti-solvent or non-solvent. Okay, and that method is known as anti-solvent precipitation. Okay, anti-solvent precipitation. And in case of chemical method, which are the different types of chemical method? Type your answer in chat box. What are the different types of chemical methods? Double decomposition. What is the which material we use for the double decomposition? Type your answer in chat box. I am telling you the name. Double decomposition. Double decomposition. Yes, arsenic oxide. That it will form a. It will, in case of double decomposition, it will form a arsenious sulfide, not arsenic oxide. It will form a arsenious sulfide in case of double decomposition. Colloid of arsenious sulfide. Okay. Colloid of arsenious sulfide is an example of comes under the double decomposition method. Then oxidation, hydrolysis, and reduction method. Okay. So that are chemical method for the preparation of lyophobic colloids. Okay. And in case of hydrolysis, the example of the iron oxide, I think, or iron hydroxide is there. So that is also covered under the hydrolysis method. Okay. And in case of oxidation method, we consider the hydrogen sulfide, I think, right? So it will covered under the oxidation method. So remember these methods also, chemical methods, which is double decomposition, oxidation, hydrolysis, and the reduction method. Okay. And the example of double decomposition method is the colloid of the arsenious sulfide. Okay. Where we use arsenic oxide with the arsenic oxide is a starting material. Okay. So arsenic oxide with the hydrogen sulfide, and it will gives you arsenious sulfide. So that's why two components we are combining. So that's why it's known as double decomposition. And as I have told you that what is the dispersion method, we reduce the particle size. Okay. Through ultrasound or different methods. Then in case of peptization, we break the aggregate same, but we use a peptiding agent. Okay, peptizing agent to reduce the particle size. Here we are using some agents. Okay, and here in milling and grinding, we are using some forces. And in case of ultrasound, we are using ultrasound energy, okay, or ultrasound waves. And here we are using a forces in case of colloidal mill, and here we are using a peptizing agent, but we are reducing the particle size. That is what the dispersion method is. Okay. Then electric arc method. This also have told you. Just remember the name of the method, and also this example, that silver and gold colloid will be prepared by this method, obviously, because in this method we use an electrode, right? Electrode of a gold or a silver, right? For the preparation of colloidal solution of gold or silver. Okay. And as it's electrode, so we use some metal. Okay. And for the example that as I have discussed, the most common one is the gold colloid. Okay. For the in case of lyophobic colloid. Okay, and that is prepared by the electric arc method. Then ultrasound, as I have told you. Then in case of condensation method, it is opposite to the dispersion method. Here what we are doing is that there is a molecular level dispersion, that is also known as molecular dispersions, are also known as true solutions, right? So molecular level dispersion, from molecular size we comes to colloidal size around nanometer range, right? So that is in case of condensation method. Okay, that is and in condensation method, chemical method is there. Okay, and also the aggregation method. As I have told you, addition of non-anti-solvent method, then chemical methods where we can see here sulfur for the oxidation, ferric oxide as I have told you for hydrolysis, arsenic oxide for the double decomposition. In this one, the product which the colloid which will form is the arsenious sulfide. Okay, that is I have written it as AS, that is arsenious sulfide. Okay. And in case of reduction, the example is gold, silver, and platinum, as I have discussed in the electric arc method also. Okay. Any question, anyone till? Any question, anyone? Remember difference between lyophilic, lyophobic, different methods to prepare lyophobic. Why methods required to lyophobic? Because they are not stable. Okay. So that's why required special methods. And the association colloids, simply you can tell association colloids is nothing but the your surfactant solutions. Okay, your surfactant solution form a association colloid. Okay, and in case of association colloid, this is your surfactant solutions, and your surfactants are also known as amphiphiles. Okay, so that is why it's also known as amphiphilic colloids. Okay, as your surfactant is both hydrophilic and hydrophobic, so that's why also known as amphiphilic colloids. Okay, and your all ionic, non-ionic, all surfactants will covered under this. Okay. And the most important thing to consider here in case of colloids is the CMC. What do you mean by CMC? In case of association colloid, the most important term is to consider is the CMC. And what is CMC? What is CMC? It is written here also. Critical missile concentration, right? And what is the definition of critical missile concentration? Is the a concentration range of a surfactant at which missile start forming. Okay, at which missile start forming. And important thing that what is Kraft point. Okay, it is also related to CMC. Type your answer in chat box. What is Kraft point? What is Kraft point? Type your answer in chat box fast. Type your answer in chat box. So Kraft point is a temperature which required to attain the CMC. Okay, or solubility or temperature at which the CMC achieves. Okay, temperature at which CMC we are able to achieve the CMC. Okay, that is the known as Kraft point. Okay, that is known as Kraft point. Okay, So see, here you can see. Okay, or solubility equals to CMC, temperature at which the solubility of a surfactant is equal to CMC. That is what I am telling. Okay. So that is known as craft point, and this MCQ was in GPAT 2022. Okay. This question was in GPAT 2022. What are the examples of ionic, non-ionic, and you can say cationic surfactants? That will be separately covered by the Payam sir or Praveen sir in the emulsion chapter also. Okay. So we will move for the important methods for the colloids. Okay, and how we can separate the colloids, right? You have a colloidal dispersion, colloidal dispersion. So to separate the colloidal particles, you require some methods, and that methods covers the dialysis, which is been simply you pass it through a membrane, then electrodialysis, where it involves the involvement of a charge also, right? It means that if a particular colloids contain charge, specifically you can consider the lyophobic colloids. Then ultrafiltration, where we use centrifugation method. Okay, and also the filters, ultrafilters, where pore size is very less. Okay, and then the purification method. Okay, sorry, these are the purification methods for the colloidal dispersion, which is dialysis, electrodialysis, and ultrafiltration. Here we are using ultrafilter. Here we use the electrodes, which it means that your colloid is charged. An example is the lyophobic colloids, and the dialysis method, which simply involves the dialysis through membrane. And the best example is your hemodialyzer, right? Because as I have mentioned, your blood is also contain a colloidal dispersion, and all the impurities which is generated in the kidney failure, because your kidney is not filtering the blood, right? Because of the kidney failure. So that particular hemodialyzer is work on this same dialysis principle, and there also the impurities which are accumulated in the blood is also in colloidal range, and they are removed by the dialysis method. So these are the methods mentioned here, which I have discussed. Here we use ultra filter, as I have mentioned, with very less pore size. Now, very important points, and then we will discuss more five minutes, and then we will end this lecture. There are three types of properties of the colloid, which is optical, kinetic, and electrical. Okay. And what will be covered in the kinetic and electrical properties? Type your answer in chat box. Type your answer in chat box. Type your answer in chat box. What are the electrical and kinetic properties of the colloidal system? Yes, Brownian motion is kinetic. Yes, zeta potential is which kind of property? Zeta potential. Zeta potential is which kind of property? It's a electrical property, right? Yes, very good. So now back to topic. We'll discuss it in upcoming slides also. Yes, Tyndall effect is kinetic. Yes. Though optical properties include the light scattering, turbidity. Okay. And light scattering, as I have explained you in the previous slides also. Right. That is dynamic light scattering. So that is also a optical property. Okay. That is light scattering. Then Tyndall effect. This is also a optical one, not kinetic. It's optical one. Okay, Tyndall effect is also optical one. And what is Tyndall effect? Is a simply and it is also due to the light scattering, because of the light scattering. Okay, it is also seen because of the light scattering. And Brownian movement, up to which particle size Brownian movement can be possible? And type your answer in chat box. Up to which particle size Brownian movement is possible? 5 micrometer. Very good. Very good. Yes, it's a 5 micrometer. Remember this, everything which I am telling, all will be a kind of can be asked as an MCQ. Okay. That is 5 micrometer range. Very good. So then Tyndall effect. Tyndall effect is simply due to the light scattering itself, right? And it's a visible path of the light will be visible. Okay. So that is your Tyndall effect. And it is also due to the light scattering. Okay, then microscopy is also a optical property, that is microscopy. Electron microscopy, then turbidity, all types of microscopy will be considered under the optical properties. Okay, and we have discussed the same and optical microscopy in the micromeritics also there, so it will be same here also. Then for the measurement of turbidity, we use two methods, that is nephelometry and turbidometry. Okay, that is nephelometry and turbidometric method. And in case of nephelometry, we measure the light intensity at 90 angle. And in case of turbidometry, we measure light intensity at 180 degree. So this is the what the difference between two. Yes, very good, Gayatri. Yes. So it's the difference between nephelometry and turbidometry. Remember this also. Okay, this will also covered under the optical property. This is not, this equation is important for the measurement of turbidity. This tau is turbidity. Hc by tau is equals to 1 upon m plus 2 bc. So this equation is important for the measurement of turbidity. Okay, remember this equation. Then kinetic properties, as I have discussed, Brownian motion. And Brownian motion, as I have also told you, up to 5 micrometer it is possible. And how can we reduce Brownian motion? By addition of which ingredient? Viscosity modifier, right? By viscosity modifier like glycerol or glycerine, we can add that, which reduce the increase the viscosity of the system, and by increasing in the viscosity, it will reduce the Brownian movement. Yes, glycerine or a glycerol. So it will decrease the Brownian movement. Okay, so it will decrease the Brownian movement as you increase the viscosity, because the Brownian movement may lead to the problem of the increase in the particle size. Okay, because of the Brownian movement, aggregation is more favorable. Okay, so that's why it is important to add viscosity modifier. Okay, remember this also. Right here mention some Brownian movement kinetic property, which is Brownian movement, diffusion, sedimentation, viscosity, and colligative properties. Then diffusion can be governed by which equation? That equation is written here. It is somewhat, I think slide is get corrupted, but I have also discussed in this one in the tablet chapter during the dissolution part. Which equation is this one? Not Noyce-Whitney? Yes, Fick's first law. For the diffusion we cover. For the diffusion it is Fick's first law. And for the dissolution it will be Noyce-Whitney equation. Okay, so this one, this equation, I think slide was corrupted, but you guys know that is Fick's first law. Okay. Then sedimentation, as we have discussed about the Stokes law also, Stokes diameter. Then the important term is the zeta potential. What is difference between zeta potential and Nernst potential? These are the some last portion of this chapter, and after we discuss one definition of gold number, and after that we will complete this session and this lecture also, and the chapter of the colloidal dispersion. What is the difference between zeta potential and Nernst potential? Difference between zeta and Nernst. Nernst potential, what you have to remember, the term is for the solid surface. Okay, if you have read the definition, right? It's regarding the solid surface, potential of the solid surface. And here, in case of zeta potential, yes, it is electrokinetic, while Nernst potential is electrodynamic. Yes, you are right. And also in case of zeta potential, it is the potential between the tightly bound layer and electrically neutral region. So where your colloidal particle is dispersed into the liquid, so that particle will cover the different layers. Okay, different layers. If it is some, for example, positively charged colloid, so it will consider cover different layers, that is positive, negative, positive, negative, and then there will be a neutral region where positive and negative charge is equal. So distance between the tightly bound layer and the electrically neutral region, that is known as zeta potential. Okay, remember this, that is known as zeta potential. Okay, and zeta potential is very important for the stability of the colloidal dispersion. Okay, so remember this also. And Nernst potential is for the solid surface. Okay, difference between colloidal surface and Stern layer. Yes, but the main term you have to remember is the solid surface. And the last term which we will discuss is the protective colloid action, or that is also known as gold number. Okay, so what is gold number is that the amount that is in milligram. Okay, amount of protective colloid. Amount in milligram. Amount of protective colloid required to stabilize your gold colloid. You are required to stabilize gold colloid when you add 10% 1 ml NaCl into that gold colloid. And as you add NaCl, that gold colloid get destabilized. So to stabilize that, we add this protective colloid, right, to prevent the color change from the red to violet. Color change from the red to violet. Okay, red to violet. So this color change we will stop. Yes, yes, very good, right? So these terms are important. 10 ml 1% NaCl, red to violet color we have to stop, because as you add this electrolyte solution, it will destabilize the gold colloid and it will start aggregating. But we, to prevent the aggregation, we require some protective colloid, which is hydrophilic colloid, right? And there are some polymers, hydrophilic polymers. Okay, and their amount in milligram. Okay, and the most stronger one is the gelatin. And because this MCQ has been asked in previous year's GPAT question paper, right? Gelatin is strongest and Tragakant is weakest protective colloid. Okay, because as the amount required for gelatin is something around 0.001 milligram. Okay, So which is very less amount. And here for Tragacanth, it's around, I think, 10 or something, right? Exactly, I'm not able to recall the number, but its amount is somewhat higher, right, as compared to all other examples. Also, albumin is also a protective colloid. Then your acacia is also a protective colloid. Okay, gelatin is also protective colloid. Okay, so gelatin is stronger one and Tragacanth is a weakest one. Okay, so remember this. And what is gold number? Any question, anyone? Till now? Any question, anyone? These are some important points of the colloidal dispersion, lyophilic, lyophobic association colloids, gold number, what is zeta potential, Nernst potential, then what are the different methods to prepare the colloidal dispersion, specifically lyophobic. What are their examples of lyophobic, lyophilic, and association colloid? And association colloid, simply your surfactant solutions, which are ionic, non-ionic, and cationic surfactants. So this is about the Schulze-Hardy rule. Schulze-Hardy rule also will be covered in the emulsion chapter also. So Praveen sir will cover that also. Okay. Schulze-Hardy rule, they will cover there also. And in case of Schulze-Hardy rule, in simple terms, if you know, a Schulze-Hardy rule is simply a ability of your cation, right? As much valency, like for this aluminium having +3 charge, Mg +2, then your Na plus. So as the higher the positive charge, higher the valency of the positive charge on that ion, so that will having the maximum capacity to destabilize your lyophobic colloid. To destabilize. Okay, so that is known as uh, Schulze-Hardy rule, right? So it will be based on its valency here, and or its positive charge. Higher the positive charge, greater its stability to destabilize your colloid. So that is Schulze-Hardy rule. Any other question? And there is also maybe a Hofmeister series. If you see in the Martin book, you will get that also. There is a citrate, then and it is for the negative charge. Okay, Schulze-Hardy rule is for the positive charge one, and Hofmeister series is for the negative charge. Any question other? Anyone? This is about today's lecture. It is somewhat longer, but as we have to cover the important chapters in this lecture, in this one lecture. So that's why we have take it somewhat long, but it will be worth it for you. Every important aspect of the important aspects I have covered, and also in your mock test, you will get some MCQs from this portion. All three portion, that is rheology, micromeritics, and colloidal dispersions. Okay. And also part of emulsion and suspension. There also Praveen sir will cover the Schulze-Hardy rule, and also the suspension part. That is suspension and emulsion will cover under the heading of the coarse dispersion. Okay. Any question, anyone? Otherwise, we just complete the session. Thank you for joining, and thank you for your patientful listening. Have a great day, and best of luck for your exam. If you have any question, you can type your question in the group that is created for you, and the organizers will forward the question to us. We will definitely answer that. Okay, so you can ask your question definitely. Any question you have regarding that? Okay. And we can also have a one kind of an interactive session, right, just before your GPAT examination, that what kind of mindset with what kind of mindset you have to bring with you in during the exam, because mindset is very important, because based on that you will select the number of MCQs, right? So thank you for joining. Have a great day, and we will may meet in one interactive session where we just take your questions regarding the preparation, right, just before your exams. Thank you for joining. Thank you very much.
Thank you so much, sir.